Okay, this is a quick video on proof by contradiction. So the idea of this proof is that we are given a statement to prove, and what we do is we assume the opposite is true. And then from that assumption, we do some maths. And after a little bit of maths, we end up at a contradiction, a mathematical contradiction, which is denoted by a little sideways hash. And because of that contradiction, that means this assumption is true. This assumption is false, which then means that the statement is true. The idea of it, we're given a statement, we assume the opposite is true, we do some maths, we arrive at a contradiction, therefore the assumption is false, and that means then that the statement is true. Okay, that's the idea behind proof by contradiction. So a couple of examples then. Proof by contradiction that there exist no integers a and b for which 9a plus 27b equals 6. Okay, so what we're going to do is we assume that there exist, okay, capital backwards E, there exist integers a and b such that 9a plus 27b equals 6. So this is me assuming the opposite is true. Okay, it's me assuming. Well, if this is true, then this implies then that a plus 3b equals 2/3. That's just dividing that by 9. A is an integer, b is an integer, and 3 is an integer. Therefore, 3b is an integer. Integer plus integer is an integer, so the whole thing there is an integer. But the problem is that integer equals 2/3. So there is our contradiction. We have an integer equals 2/3. Well, that's obviously not true. Therefore, my assumption is false. Therefore, there exist no integers a and b such that 9a plus 27b equals 6. Another example is, this one's quite a common one to use. Prove that root 2 is irrational. Prove that root 2 is irrational. So I'm going to assume the opposite is true. So I'm going to assume that root 2 is rational. Okay, now a rational number is one that can be written as an integer divided by an integer. So I'm going to say P on Q, such that P and Q are integers which share no common factor. Okay. So for example, if it came out to be 2/4, that would obviously be just a half. Share no common factor. Okay, that's what it means for a number to be rational. So what I'm going to do is I'm going to take this equation then, and I'm going to times it by q. So I end up with root 2q equals p, and I'm going to square it to give me 2q squared equals p squared. So this then implies that p squared is even, which in turn implies that p is even. Okay. If p squared is even, then p is even. So if p is even, then I can write it as 2 times an integer, where n is an integer, so n is an element of the integers, and I'd repeat the process. So root 2 equals p, which is 2n on q, times both sides by q. I get root 2q equals 2n. Square both sides. I get 2q squared equals 4n squared. This implies that q squared equals 2n squared. This implies that q squared is even. Okay, because you're taking an integer and you're timesing it by 2, so therefore q squared is even. That then in turn implies that q is even, which is a contradiction. Okay, we have established that p and q are even. Okay, if p and q are even, then they both share a factor of 2, which contradicts this statement. Okay, we are assuming that p and q do not share a common factor. So therefore p and q are even, so that's a contradiction. So therefore root 2 is irrational. And that's the end of the proof. Thanks for watching.